So today's speaker is Dong Lin, and he received his bachelor's degree in space physics from the University of Science and Technology of China in 2011, and his master's degree in space physics from University of Chinese Academy of Science in 2014. And then he received a PhD in electrical engineering from Virginia Tech in 2019 before becoming an ASP postdoc within HAO. And recently, this past January, he was promoted to project scientist in HAO, and he's a member of the CGS modeling team, and his primary work is on characterizing auroral precipitation and magnetosphere, ionosphere, thermosphere coupling. And today he will discuss subauroral polarization streams, intrinsic response of geospace during storm time. So go ahead, Dong.
Okay, thank you, Nick. Hi, everyone. Hope everyone can see my slides well and hear me well. Okay, so yeah, this is actually my second time to give a colloquium at the HAO. Last time it was more than 2 years ago in February of 2020. And I remember it was the last one before the pandemic. I was trying to give an in-person colloquium today, but unfortunately the technical support is not fully available yet. However, as you know, NCAR is entering the green phase this week, and I'm in HAO in person right now. So I hope this can be a good connection, and everyone can go back to normal life soon. So yeah, in the past 2 years, the pandemic has changed a lot of things, and like here we have colleagues come and go, and one of the most exciting progress from our team is probably this NASA Drive Center for Javaspace storm. It was recently selected to enter the phase 2. What I'm talking about today is also very related to the activities occurring in CGS. So yeah, I'm going to discuss the so-called SAPS or subauroral polarization streams. Excuse me. Mostly this is with the help of the newly developed major model and also with available observations. So this is a brief outline. So basically, the talk today consists of 3 studies. The first one is about the role of the diffuse electron precipitation in the formation of SAPS. The second study is about the dawn-side SAPS occurring during major geomagnetic storms, and the last one is about the variability of SAPS on the MFBY. So the first study was published last year in JGR Space Physics. The second study is under review in AGL Advances. The third one is the ongoing one. Okay, so let's start with a overview of the geospace in the Helisphere. So as we know, the geospace is actually under the influence of solar activities all the time, including solar flares, coronal mass ejections, and the energetic particles. So the interactions between, so as we know, the solar eruptions can cause magnetic storms in the geospace, which are actually impacting many aspects of human life and society, especially in modern days. So it's actually very necessary for us to have good knowledge about how the geospace behaves during the storm time. As we take a closer look of the geospace, it actually consists of many different regions as a result of the interactions between the solar wind and the geomagnetic magnetic field. For example, the magnetopause is actually the boundary of the geomagnetic field. And also, as they get closer to the Earth, there are energetic charged particles make up the so-called ring current and the radiation belt. And the magnetosphere then got connected to the top side of the atmosphere through the magnetic field lines. Of course, with exchange of mass and the energy and so on. So the different regions in the geospace are actually coupled as a system, making it very challenging to fully understand the processes going on. So here at NCAR, the National Center for Atmospheric Research, many of us are particularly interested in the atmosphere. So the upper atmosphere of ionosphere thermosphere consists of many plasma and neutral structures and processes across a broader range of spatial and temporal scales. For example, in this highlighted ionosphere, the large-scale plasma convection is driven by the forcing from above in the magnetosphere. And also, like on the other hand, as the plasma got transported across the polar cap, they can break into small-scale irregularities, which can interfere with our radio communication. So the broader range of the structures and the dynamics occurring in the IT, making it requires us to have a systematic understanding, systematic approach to deal with the interactions between the different geospace regions. So the so-called SAPS, subauroral polarization streams, is one of the most typical structures in the geospace. And it's particularly interesting because it's on the so-called mesoscale. And in the context of the ionosphere thermosphere, this is like between 50 to 500 kilometers. And SAPS actually have been widely observed by various observational facilities. For example, here is the measurements from the DMSP satellites. And this is separate measurements by the super high frequency radar. And also with the incoherent scattering radar, it can be also often detected. So the definitive feature of SAPS is that below this auroral boundary, there is always what is often a separate flow channel westward with a magnitude of a few hundred to a few kilometers per second. So it's very persistent and relatively narrow range. And so it's supposed to imply the interactions between the different regions in the geospace. More importantly, based on the studies so far, we have learned that SAPS are actually connected to a number of different aspects in the geospace. For example, they are known to be related to the closely related to the field and current that are connecting the ionosphere and the magnetosphere, which is then connected to the injections from the plasma sheet. It also has to do with the local conductance and plasma flow structures here in the ionosphere. And if we go further down, there have been reports about the SAPS effects in the thermosphere winds and so on. So SAPS definitely has have a lot of implications of different aspects in the geospace. That's why we would like to have a good understanding of it. So just like I mentioned in the very beginning, we just got selected of this Center for Geospace Storm. And one of the critical science themes of CGS is to explore the mesoscale structures in the ionosphere and including its global effects. And just to a little bit of advertising, the vision of the CGS to transform the understanding and the predictability of space weather. One of the staple product of CGS is this so-called major model or multi-scale atmosphere geospace environment. This is a grand blueprint, as you can see, including like a global solver and of the entire ionosphere. So the ultimate goal is to understand the entire geospace from a scale of like 20 kilometers to the range of 2 million kilometers of the entire magnetosphere with such a state-of-the-art geospace model. Okay, so let's move on to the first study. regarding the role of the diffuse electron precipitation in the formation of SAPS. So actually, there have been attempts of using geospace models to simulate SAPS in the community. For example, here I'm giving 3 examples of the well-known community models, including this LTR model from our own group, but it was kind of developed before the CGS project. So as you can see, one of the main insufficiency of all these models is that the mesoscale subauroral channel is actually not resolved so well in any of these previous models. Based on the what I've learned about the driving physics, a very important factor is actually about the very delicate processing of the precipitation and so that the conductance in this subauroral region. So in the past 2 years, namely in the phase 1 of CGS, what we have achieved is this version 1 of the major model. So basically, it consists of the Gamera global MHD model of the magnetosphere. Basically, this is an upgrade of the well-known airfan model, and it's two-way coupled with a ring current model called RCN, rest convection model. So basically, this is because in the inner magnetosphere, the MHD is no longer a good description of the plasma there, and these magnetosphere models are coupled via this remix module, which is again two-way coupled with TIDCM, a general circulation model developed here at NCAR. So all these different modules are two-way coupled with each other. One of the critical features in the Major 1.0 is that we have adopted a more comprehensive precipitation, basically that consists of the so-called monogenetic electron precipitation from the MHD parameters from the Gamera model, but we also derive the diffuse electron precipitation from the RCM model. So basically, this is physically determined by the generation mechanism. So the monogenetic is more determined by the large scale voltage and the current relation, while the diffuse precipitation is caused by the wave particle interactions. Thus requires a kinetic description. So now with this new coupled model, let's see how it performs in simulating SAPS. Here is what we got in an event simulation of the 2013 St. Patrick's Day storm. And here we made some comparison with DMSP satellite. As you can see, here the SAPS channel below the auroral boundary is very well resolved. I will show a comparison with previous results in a later slide. Again, did I hear anything? Okay. So again, this is just like a 1D view of the SAPS with data validation. With the model results, we can take a 2D view of the distribution in the ionosphere. Like here, this panel top left is showing the westward ion drift. As you can see, the SAPS is just manifest as a separate flow channel below this auroral boundary. The magenta line is the auroral boundary, which is, as you can see, in the bottom left. So just to mention that this is an energy flux of electron precipitation, and you can clearly see separate. This is so-called monogenetic, and this is so-called diffuse. Again, they are coming from two different physical mechanisms. So again, with this newly developed major model, we can now resolve the mesoscale substructure with much better reliability. So as I just mentioned, we used to be able to resolve SAPS with the older model as well, but it doesn't seem to resolve the mesoscale structure as well as what you just saw with in the new image model. For example, the bottom row is in image we used the default presentation, which is called a feather. This is essentially the same presentation model that we used in LTR, if you can recall the one of the paper I just showed in the introduction. So the default presentation in RFM or LTR was purely based on the MHD parameters. That's not so good at resolving the actual location of the diffuse precipitation. So this is like a demonstration of how the a good characterization of the diffuse precipitation is important, especially in resolving the mesoscale structures like SAPS, as we're talking here. So another controlled experiment is here. If we just fully turn off the diffuse precipitation, which is doable in the simulations, then the entire subauroral flow is just like a very broad channel without resolving these mesoscale structures, as you can see in the baseline run. So to wrap everything up, we can see that this picture is to illustrate the driving mechanism of SAPS. So basically, again, you see this mesoscale channel in the ionosphere, and if we just map everything to the magnetosphere in the equatorial plane, particularly if you just look at these boundaries and their projection in the magnetosphere. So basically, the SAPS is formed between this equatorial boundary of the electron precipitation and that of the downward region 2 phase line current. And back to the magnetosphere, it's essentially because of there's a gap between the inner boundaries of the source region of the electron precipitation and that of the region 2 phase line current. And this is essentially determined by the different depth of the ions and electrons in the recurrent and plasma sheet, which have to do with their energy-dependent drifts. So as a brief summary, so in this study, we have used this fully coupled geospace model of image to capture the key physical mechanism in the formation of SAPS, when we have also resolved the very distinct spatial structure of subauroral polarization streams. This is a big advance, especially compared to the previous results we got using the LTR model, for example. And the success should be attributed to the new presentation, which deal with the diffuse and monogenetic separately based on the distinct driving physical mechanisms. We also explored the evolution of SAPS in the ionosphere and the thermosphere in this study, and you are welcome to check out more details from this paper. So next, let's move on to the next study if no questions. Okay, hearing now. Okay, well, actually, we started the third study first, but during that time, we found that this new phenomenon of the dawn side SAPS more interesting, and this paper was submitted before the third one. So let's take a look at what that means. So, well, as we know, statistically, the SAPS are more preferred towards the dusk side. So like here, the largest average ion drift velocity is near 16 or 18 MLT, and as it moves toward the midnight or even the dawn side, is getting weaker and weaker. So you may sometimes see the westward flow channel in the dawn, and but again, that just means it's a extended westward flow channel. And the latitude of the channel also goes low as it approaches the midnight sector. And the preference of SAPS occurrence in the dusk side is essentially determined by two factors. So first of all, as we know, the basic driving mechanism involves that little gap between the auroral boundary and the downward region 2 field and current boundary. And think about the source of these two. I mean the field and current and the precipitation. So the field and current is mostly determined by the azimuth pressure gradient in the ring current, which consists of the energetic ions. And you know the ions typically drift westward. That's why the ring current distribution and consequently the region 2 field and current has a asymmetry toward the dusk side. But on the other hand, the electrons in the magnetosphere tend to drift eastward because of the opposite sign. So the electron precipitation tends to be more favored in the midnight to dawn sector, which is also well known and has been demonstrated in statistical results. So we combine these two, namely the lower boundary of the region 2 field and current. This is a ring current though, but just to show the relative location. The low latitude boundary of the region 2 field and current goes to below that of the electron precipitation, then you should expect that a gap to occur more preferentially in the dusk sector. So this is kind of a very natural result because of the opposite drifting paths of ions and electrons in the magnetosphere. That's why we typically see SAPS on the dusk side. However, in a very recent study, actually two studies from last year, so these authors reported the dawn side SAPS during this event in 2003, November the 20th. So the difference between the dawn side SAPS and the dusk side is that the dusk side SAPS flow westward. But the dawn side SAPS are flowing eastward. But if you look from the top, they are both sunward. If we have to find something in common. So again, if you look at this DMSP measurements, this is the auroral boundary based on the energy spectrum from the electron precipitation. So this is just a typical and a well-identified dusk substructure, but the dawn side has also a substantial flow in the subauroral region, and just similar to the scenario on the dusk side, on the dawn side, the flow is along eastward. So basically that implies the electric field is equatorward rather than poleward. And it also corresponds to a region 2 field and current, which is upward rather than downward. So here we are using the image model and observations trying to figure out what was going on and what causes the dawn side SAPS. So this is just a brief overview of the solar wind conditions during this day. So this is also a very famous superstorm. As you can see, the CMH minimum reached almost -500 nanotesla. And this is just one solar cycle after the well-known Halloween, the Halloween storm. And the solar wind speed reached like 600 kilometers per second. And probably most striking feature is this MBZ of -50. I think this should be among the top ranked strong storm events in recent histories. Okay, so this is what we try to reproduce, what you just saw with DMSP measurements. Based on the first study, we are now confident in the SAP structures resolved with our major model. So here is just a sampling along the DMSP trajectories. And this color bar is the zonal ion drift. So the dark blue means it's strongly westward, and the red is strongly eastward. So just do this 1D comparison first. And here the magenta zone indicate the Subauroral, and this Phelan current, the greenish shading is for the Phelan current. And here, as you can see, we reproduced the typical dusk SAPS, and again, it's westward here. If you look at the location right here. And also, we captured the eastward SAPS on the dawn side, just like here. And this 2D view is probably more illustrative if you can if you compare these boundaries. So here the magenta curve is just the aurora boundary based on a threshold of 0.2. The value of the threshold doesn't really change it too much. The green and the cyan curves are the downward, sorry, this is the upward and the downward region 2 Phelan current boundary. So this is just like a typical scenario we have been talking about for the typical SAPS on the dusk side. So namely, the Phelan current boundary goes to below the aurora boundary, and as you know, there is a low conductance gap here, and the current color requires a enhanced poleward E field, which drives the E cross B along the westward direction on the dusk side. So similarly, this Phelan current again is upward, so you expect the a equatorward E field, which then drives the eastward SAP. So this is like the typical scenario, and it's very well reproduced by our model. So next, we try to understand when the dawn side SAPS would occur. Just using the same event, we compared different stages during the storm. This is like 2 orbits of DMSP F13 on this day. The first orbit was around 6:30 UT, and the second was around 18:30 UT. So I have to emphasize this because we'll also be using similar values for the MLT later on. But just compare the evolution from 6:30 to 18:30. You can see that even though it's very early in this storm event, we still see a very clear identified SAPS signature in both these DMSP measurements and our major simulations. And by the way, this is the DMSP measurements, and the second row is the sampling from major results. But you don't see any dawn side signatures on the around the 6 MLT on the dawn side. If you take a closer look at the different boundaries, this is just because even at this early stage, the region 2 Phelan current boundary is still way below the aurora boundary. So that's where the SAPS form. But the dawn side just got very close to each other. However, in 12 hours or 18 UT, this basically near the minimum or the peak of the storm activity. You can see the equatorward region 2 Phelan current boundary is much lower latitude compared to the auroral boundary. And so basically that means from relatively quiet times to storm time, together with the auroral expansion, this magenta line, the field and current boundary also expanded equatorward. It's just like on the dawn side, the field and current boundary expanded by more than the auroral boundary, which resulting in the formation of the dawn side SAPS. It's also reflected in the pressure distribution in the magnetosphere. Again, this the pressure azimuthal gradient, the azimuthal gradient of this pressure distribution is supposed to be directly related to the region 2 field and current that we are seeing here. And also, as you can see, the upward region 2 also got enhanced and over a large spatial range. So next, we try to sample the ring current pressure at these two different MLT, one on the dusk side and one on the dawn side, so that we can have a continuous picture about the evolution. And as you can see, on the dusk side, the ring current pressure build up just started as soon as like a 5 UT. This is basically when a very minor southward BZ arrived at the Earth. And this tens of kV basically consists of most of the ring current pressure. However, the dawn side is showing a very interesting transition much later than the dusk side. So you don't see substantial enhancement of the ring current pressure on the dawn side until sometime later. And at this point is when the 9 UT is when the solar wind speed has greatly enhanced from like 400 to more than 600 kilometers. So this picture is telling us the dawn side pressure build up has to do with the level of the driving condition. So we take a further look at the energetic particle, charged particle behavior, mostly the ions, because that's the main species of the ring current pressure. So this plot shows the ratio between the electric drift and the magnetic drift of ring current ions. So basically, as we know, charged particles, or let's just talk about the ions in the magnetosphere. They undergo both the so-called E cross B drift, but also the energy-dependent magnetic drifts because of the non-uniformity of the magnetic field. And during their transport toward the Earth, we can make a simple assumption of adiabatic. So there is like in our major model, the RCN assumes is adiabatic and assigns a energy invariant for each channel. So and also as the particles get closer to the Earth, their kinetic energy increases. So this plot shows the ratio between the two drifts, the electric drifts and the magnetic drifts, the speed, and then I converted it into a log scale. So basically, the positive values mean it's dominated by electric drift, like most of the outer magnetosphere. And again, as particle energy increases, the energy-dependent drift becomes dominant. So that's why it turns negative. You can also mathematically just describe by this equation for the two drifts. So what this is telling us by comparing the two UTs, the 630 and 1830 for the same energy channel, is that at a little bit earlier stage, when the convection is not so strong. As you can see, most particles in this channel, or most ions with this energy invariant, will be dominated by magnetic drift. So in other words, between these two circles, when the particle ion energy reaches 10 keV, their motion is just dominated by the energy dependent drift, which is westward. So that's why you see the dusk side pressure build up started very early. However, at a later stage, when the convection becomes too strong, the particle motion is also overturned. Like here, when the particle energy reaches 10 keV, their motion is instead dominated by the electric drift, which brings a lot of them towards the dawn side. That's why you see the pressure build up started later on the dawn side. And equivalently, we can express the trajectory using the so-called effective potential. And the contour of this potential basically suggests the trajectories of the energetic ions. This is also illustrating like a number of the energetic ions reach the dawn side. So basically, this is from the perspective of particle motion to explain why we had the dawn side ring kind of pressure build up, and consequently the formation of the strong region 2 field current and the dawn side SAPS. So we also used the chimp model or test particle model to verify the trajectory, which is shown here. So again, at a bit earlier, 6:30 UT, most energetic ions just get to the dusk side and result in the dusk side SAPS between this region. And on the dawn side, the boundaries are very close to each other. But during strong convection conditions, a number of them can get to the dawn side, so pushing the upward region 2 field current boundary more inward than the auroral boundary. That's when we saw the dawn side SAPS occurred. So as a brief summary, so in this study, we just found the dawn side SAPS occurred during the main recovery phase of major geomagnetic storms when the magnetospheric convection level is very high. What I didn't show is that I did double check several other major storms, and we do see the dawn side SAPS in a number of them. And in the controlled experiments, by reducing the magnitude of the IMF, the dawn side SAPS just disappear because the overturning of the magnetic to electric drift could not occur in that case. And the cause of the dawn side SAPS is just has to do with the transport of the energetic ions and the dependence on the energy and the electric drift. So this we think this is a very interesting and probably a significant finding, especially it can prepare us better for severe space weather events during like a extreme geomagnetic storm. So this paper is still under review, but we have an open archive version available. Yeah, and you're welcome to check out. So the last one is about it's an ongoing study. We try to understand the variability of SAPS on the MFBY. So so by surveying the literature, it seems there hasn't not been too many studies about the dependence on of SAPS on the MFBY component. A very old one was more than 20 years ago. Most recently, Urchat used a the ISR data for a statistical survey. But basically, the conclusion is kind of consistent. SAPS are statistically stronger under negative BY compared to positive BY. Well, just consider the background I mentioned in the second study. SAPS does have such a preference between dawn and dusk. Therefore, we should expect some asymmetry or some different behaviors on the positive and negative BYs. SAPS is essentially the subauroral flow, so it may be regarded as part of this large-scale convection, and this pattern is probably much better known. I mean, the dependence of the two-cell or multi-cell convection pattern on the MF orientations. Just to save some time, we also know MF direction or MF BY has a important impact on many different aspects in the geospace. For example, the reconnection on the magnetopause and the precipitation, phelan currents, and so on. So here we just used an event study trying to explore the BY dependence of SAPS a little bit. So this event was on the 24th October 2011. There was a very nice period with dominant BY of up to 20 nanotesla when the BZ was kind of negligible compared to this BY. So we try to understand what the SAPS is like under the BY dominant conditions. So these are like two orbits from DMSP F16 and F17. The plotting style is consistent with what I just showed in the second study. But the very important, a very interesting feature is that, so first, these two satellites were separated by about 15 minutes in UT. So F16 detected some sub-signature here. However, in 15 minutes, the F17 detected a much more separated SAPS channel in the Subauroral. And just looking at the MF condition here, it seems to have to do with this. Well, BY was kind of a dominant background, but BZ has decreased from like a -5 to very small value in southward. So we used the simulation results to understand the behavior between these two satellites. So again, there's a very strong positive BY as a background, and the BZ has some decreasing or weakening southward. So basically, the convection pattern is very much rotated toward the pre-noon sector, as we can expect for a large positive BY. And here, if you just look at the SAPS distribution, together with this convection cell, the location of the SAPS also shifted toward a much earlier MLT. And the gap between the channel to the major aurora return flow is also very large. Here it's as much as 10 degrees. Well, because the DMSP satellite has an orbit period of like 100 minutes, so we don't have a contemporary observation in the southern hemisphere. But because the MF was kind of stable, so just by taking a little bit, well, yeah, this is like 215. Just by taking the results from an hour later in the southern hemisphere, you don't see as large separation of the SAPS from the auroral boundary or the major auroral flow. So if let's just take a look at the assimilation results. So as we know, the southern hemisphere is kind of opposite to the northern hemisphere in terms of BY response. So but not exactly a mirror symmetric. So the convection cells in the southern hemisphere rotated toward the dusk side, sorry, the post-noon sector. So the location of the SAPS moved toward a later MLT. So that's why, like in this plot, when the satellites were around, sorry, here, around the 20 MLT, or yeah, around 20 MLT, they still have very close to the auroral boundary, which is not a so typical if you consider the northern hemisphere case. Well, so since this is still ongoing, so I'm not talking too much about it. Just to quickly wrap up. SIMF has a dominant BY component, we should expect the SAPS respond together with the large scale convection, so that they would the location of the SAPS would rotate either toward an earlier or later MLT. And the northern hemisphere and the southern hemisphere have kind of opposite pattern in terms of the BY response. But more outcomes are to be expected. So yeah, I think probably time to give a summary. So basically, we know SAPs are a typical mesoscale structure in the ionosphere, especially during storm time. And we're glad that the fully coupled image model has performed very well in terms of simulating the SAPs, including its dynamics, the fundamental driving mechanisms, and the variabilities. We demonstrated the critical role of the diffuse precipitation in determining the mesoscale structure. We also explained when, how the downside SAPs are formed and when to expect that. Probably something to keep in mind for preparation of extreme spatial weather events. And the SAPS variability on MFBY is something interesting that I'm still working on, but there are actually some more explorations going on in this group. For example, what's the exact effects of SAPS in the ionosphere and the thermosphere, and how that's related to the so-called like abnormal SAPS and penetrating electric field and so on. So I think I should stop here, and happy to take any questions. Thank you.
All right. Thank you, Dong, for the presentation. Does anyone have any questions? Lee?
Yeah, so Dong, is the diffuse electron precipitation, does that happen during the non-storm time, or maybe at like very weak activity?
Well, I think it does. I mean, I think the separation of storm and non-storm is probably, people can easily to debate on that, but definitely it's just like the magnitude of the diffuse precipitation expected less during relatively quiet times.
Okay.
Yeah.
So then does this mean that the SAPS can be seen during the non-storm time?
Well, actually, there have been reports about the so-called quiet time middle latitude convection. So what I cannot say is absolutely non-exist. It's just I think the key point is that for the SAPS to occur, it needs to satisfy such a condition that the phelan current boundary goes below the auroral boundary wherever they are. So that's it's like a more of a relative sense between these two boundaries. Yeah.
Okay, thanks.
Yeah.
Yep. Ling, do you have a second question, or?
No, I tried to lower my hand.
Okay. Yeah, that's what I thought, but wanted to make sure. Are there any other questions? Astrid?
Yeah, Dong, very interesting. So you mentioned, I mean, this is a mesoscale feature. Can you say something about the resolution which is needed in mix and the magnetosphere and RCM?
Right. Thank you for that. Yeah. Probably I should have included that. So yeah, in this case, we use a so-called quad resolution. So that means in remix, it's 1 degree by 1 degree in longitude and latitude. The Taycan was 1.25. And in Gamera, it's like 0.2 RE near the inner boundary. So, well, since a typical SAPS is like a few degrees in terms of latitude and width, so this 1 degree is sufficient, but we can also carry out a higher resolution, like a 0.5 degree resolution, yeah, to explore the even smaller scale structures. I mean, or to resolve the SAPS better. Let's put it that way. But yeah, 1 degree is just a standard resolution right now.
Any other questions for Dong? If not, then I will ask one. In the last part you show with the hemisphere asymmetry, is there any observational result showing this, or is this so far kind of just what you see in the model?
I don't think it's just something in the model. Definitely, at least from like statistical results, we should expect the rotation of the convection cells under different, I mean, on the same BY, but in northern hemisphere and the southern hemisphere. But indeed, for SAS, cause like a DMSP, they always has this orbit period issue. It's not necessarily an issue. It's just it's just like a systematic design nature of that of this kind of measurements. Yeah, well, I tried to use the Subauroral data for this kind of comparison, but seems the southern hemisphere does not have enough sufficient coverage, so makes another challenge. But I think this year is a good event because, as you can see, the MF has been very stable. So I would assume the comparison between this 2 or 4 orbits would be a good one, although more careful examination is definitely needed. Does that answer your question?
Yes.
Okay, great.
Astrid, do you want to go ahead?
Yeah, thanks. This is a very naive question. So are the SAPS, are they on open field lines or closed field lines if they're subaurora? I mean, you need RCM, so isn't this closed field line region? So is the north and the south then conjugate?
Yeah, they are on closed field lines. Cause well, it has to be in the regional field line current. So that's yeah, it's on the closed field lines. There have been studies regarding the conjugacy of SAPS between the northern hemisphere and the southern hemisphere, but it's based on assumption that it's fully equipotential. Yeah, I think you can check out probably the paper by Burak Kunduri. He did that. Well, actually, Burak gave the talk a few weeks ago here at the colloquium. I believe he mentioned that a little bit.
Okay, yeah.
Right.
Liang? Go ahead.
Yeah, so you probably already talked about this, but I might have missed it. So it's the, like how often, like when we observe the SAPS, so how often it's like dusk side, how often it is like downside?
Well, yeah. So I would say so far people have been talking about SAPS. I mean, when people talk about SAPS, they are referring to the dusk side uniquely so far. The dawn side, as we explained here, it requires a very strong magnetosphere convection or very strong driving condition to occur, so that the magnetic drifts can be overturned. The first report was just last year, and we are here first to explain that. I think it would be very interesting to do a statistical survey about how often they occur, but definitely much lower occurrence rate than the dusk side, because you don't always have such major storms.
Is like even like during the large storm, it's not necessary. You're not necessarily be able to see the downside steps. So
Well, yeah. So yeah. Again, so for the dawn side to occur, it's kind of like a competition between the magnetic drift and the electric drift. I mean, the level of the storm activity is definitely very related to whether it can or cannot. But more quantitatively, probably we should compare like this, like when the electric drift is substantial enough to dominate over the magnetic drift. I haven't got a chance to do a statistical survey yet, but that's very interesting, and we're also looking forward to that.
Okay, thanks.
Yeah. Thank you.
All right, last chance for any questions. If not, then thank you again, Dong.
Thank you, everyone.